Good afternoon, everyone. I am Catherine Brookman, Associate Director, Knowledge Transfer and Exchange, and on behalf of Dr. Jack Callahan, Director of the Center of Research Expertise for the Prevention of Musculoskeletal Disorders, or CRE-MSD as we are more commonly known, we'd like to thank you for joining us today. This webinar is the first webinar in a series that we have partnered with the Association of Canadian Ergonomists, or ACE, as they are more commonly known. Alice Stevens, professor at Fanshawe College and ACE's webinar coordinator, is joining us for these webinars and will facilitate the question and answer period. We are grateful to the Ontario Ministry of Labour, Training and Skills Development for our funding, which supports the delivery of these webinars, and to our presenters and collaborators who provide their expertise. We are using a new webinar presentation platform, and therefore we ask that you keep yourself muted for the duration of the webinar. Please use the microphone icon in the floating control panel that appears near the bottom of your screen. Please use the chat feature to communicate during the webinar. The chat box can be pulled up on your screen by selecting the chat icon in the floating control panel that appears near the bottom of your screen. This webinar will be recorded, with the recording being made available to you on our website in the near future. Shortly after today's webinar, you will be provided with a copy of the presentation slides along with an evaluation. Please fill out this evaluation as it will assist us in our future delivery of these webinars. The format of today's webinar is as follows. The presentation will be given, after which time we will have 10 to 15 minutes for a short question and answer period with our presenter. We ask that you type your questions into the chat box at this time, and Allison will relay these questions to our presenter. Should you have a pressing question or issue, such as a technology glitch that cannot wait until the end of the presentation, please type this into the chat box and we will do our best to address it right away. Now it is my pleasure to introduce to you our presenter, Dr. Kayla Fewster. Dr. Fewster is currently working for CRE-MSD as a research associate on the MSD prevention guideline. Dr. Fewster completed her master's degree at McMaster University under the supervision of Dr. Jim Potvin, with a focus in occupational biomechanics and proactive ergonomics. She then completed her doctoral degree at the University of Waterloo under the supervision of Dr. Jack Callahan, Director of CRE-MSD, where she specialized in lumbar spine biomechanics. While working under the supervision of Dr. Callahan, Dr. Fewster has led the opportunity and had the opportunity to collaborate with industrial partners, including the Infrastructure Health and Safety Association, who were partners along with the Ontario Ministry of Labour, Training and Skills Development in the research being presented today. Now it is my pleasure to turn this presentation over to Dr. Fewster.
Thank you very much for the introduction, Catherine, and thank you everyone for attending this webinar today. I'm very excited to be presenting this work, which was completed, as Catherine mentioned, with in collaboration with IHSA, the MLTSD, and CRE-MSD at the University of Waterloo. While this area of research wasn't particularly in my wheelhouse, when I heard about this project coming through, I thought it sounded really cool and interesting. And now that we've completed it, I can definitely say that it more than delivered. As I've said to IHSA previously when we were discussing the results we found here, this was one of the most fun yet terrifying studies that I think I've ever worked on, or probably ever will have the chance to work on. So in today's webinar, I'm going to show you what this study entailed and some of the results we found in terms of ladder safety and a new possible method that might be a possibility for ladder fall safety in terms of tethering off for the operator using the ladder. In addition, I will also walk you through a number of considerations and issues that we discovered when trying to take a potentially very violent workplace event from the field and bring it to a controlled experimental setup while still trying to take into account some of the variability you'd see in the field. While the issues here don't necessarily directly link to MSDs, I think there's a lot here that can be taken away in terms of improving and conducting research on workplace safety. So to get started, ladder-related falls continue to be a safety concern. When looking across all occupations in Canada, an average of 66 emergency room visits for ladder-related falls occur per 100,000 workers. Ladder-related falls are the leading cause of fatal falls, with up to 63% of such falls resulting in a significant injury, such as a fracture or sprain or fatality. Falls from ladders are common to all trades, but pose one of the most serious safety problems in construction. Each year, more than 300 lost time injuries are caused by falls from ladders in the Ontario construction industry. Many of these falls result in critical injuries or fatalities. Across all industries, construction has the largest occurrence of ladder-related falls. In terms of age categories, adults between the ages of 40 and 65 have the highest rate of incidence. And males account for nearly 85% of all incidents. There continues to be a high number of incidents where workers have fallen from ladders and were critically injured or killed on construction projects. The following table was taken from the IHSA website, and it shows the number of events investigated by the MLTSD's construction program between the years of 2011 and 2017. 13% of critical injuries and 4% of fatalities investigated by the construction program over this period were directly related to ladder use on projects. So currently, the Infrastructure Health and Safety Association dictates that when working from an extension ladder, the ladder itself must be anchored to a surrounding structure at a fixed anchor point, with the side rails extended additionally a minimum of 3 feet above the anchor point. So here I kind of just have an image on the screen showing you that this would be a typical setup for when a ladder is set up for use. You can see here that the ladder is then tied off and then extended an additional 3 feet above the secure tie-off point. In addition, if a worker is working more than 10 feet off the ground, they must also wear a safety harness and tie off to a well-anchored lifeline or support and not to the ladder itself. However, when working from heights, it can be difficult for the worker to locate a secure anchor point to tie off to. This can result in improper safety harness use or even not using the safety harness at all. Since by law, the ladder itself must be anchored to a secure structure, it is possible that in the case of a fall, a worker may be safely restrained when tethered to the ladder as opposed to a structure or lifeline. And so this was the objective of this investigation, to see if a ladder could adequately restrain a worker if a fall were to occur, in the case that the worker was tethered to the ladder. So the purpose of this investigation, as I kind of just mentioned, was to establish safety criteria to determine the failure tolerance of a ladder with a falling 250-pound operator falling from the ladder. Because ladder use in industry can be extremely variable, we wanted to look at a number of different parameters surrounding ladder use that could lead to possible ladder failure through tipping, deformation, and destruction that could cause an operator to contact the ground with a fall arrest system attached to the ladder specifically. So ladder use in industry can be extremely variable. So one of the objectives of this investigation was we wanted to try to include a number of different parameters that could possibly influence if the ladder would potentially fail or lose stability in the event of an operator fall. And for the duration of this this webinar, when I'm speaking towards an operator fall, I'm going to be speaking towards it if the operator were falling and tethered off to the ladder. Some of our initial thoughts or concerns when designing this study were, would it matter how the operator had tied off to the ladder? For example, if the operator had simply tethered around a ladder rung versus fully wrapping around the structurally sound rails. would it matter what surface the ladder was leaning up against? For example, if a worker was working in a scenario where the ladder was erected up against a brick house versus a wooden structure, that kind of thing. And how would this influence the stability of the ladder during that fall? Similarly, would it matter what the ground surface was that the ladder was leveled on? For example, setting up a ladder on a wooden deck versus loose earth on a construction site. And lastly, how the operator fell influence the ladder failure. For example, if an operator fell straight down in the case of a fall, or if they tried to kick off while they were falling, would that matter? And would that link back to whether a ladder would fail or not? So all of these parameters were considered when designing this study with the overarching goal of gaining an understanding of if a worker could avoid impact from the ground in the case of a fall. So for the experimental setup of this study, across all conditions tested, all ladders were set up following Ontario regulations for extension ladder use, which I kind of just, I'll just briefly go over again. So all the ladders tested were set up in the exact same manner. The ladder angle was set as a quarter of the length of the extended ladder. The total extended ladder length was 18.5 feet. And this was kind of dictated based on the space that we had for our experimental setup. Then the vertical height of the building contact point was set to 14 feet above the ground. So here you can see in the image. And the ladder was resting against a sound structural beam that connected between two walls. And from this, the ladder was then tied off here at the structural beam and extended an additional 3 feet as per regulation. The operator tether was secured to the ladder at 16 feet, representing a worker's feet located at approximately 4 meters. All test configurations were evaluated using both a fiberglass and aluminum ladder. All ladders were of type 1, grade 1 duty rating with a maximum capacity of 250 pounds. A grade 1 ladder was chosen as in Ontario, this is a minimum requirement for industrial use. So based on this ladder class that we chose to use, we simulated a 250-pound tethered operator falling from the ladder because this is the weight limit that these ladders are rated for. As I previously mentioned, currently in Ontario, if a worker is working above 10 feet on an extension ladder, the worker needs to tie off to a physical structure. In this scenario, the worker would be wearing a body harness, as you can see here in this image that I've provided, which would then be tied off to a tether, which would then be tied off to the physical structure. So in this investigation, we're investigating if it would be sufficient to tie that tether off to the ladder as opposed to a structure. So here, during the experimental setup, we're focusing on the tether to ladder interface and not the body harness that the worker would be required to wear. The same tether was used for all drop testing that was completed. The tether consisted of a 6-foot adjustable lanyard. It was, for the case of this investigation, it was adjusted to 4 feet. It was a non-shock absorbing tether for a worst case scenario, and it was made with polyester webbing. And I've just kind of listed here the manufacturer for the lanyard that we use. The simulated operator tether was secured to the ladder using 2 different methods. So the first method that we tested was wrapping the tether fully around the outside of both vertical side rails and over an adjacent rung. So you can see here in the image, this is how that setup would be set up for each of those drop conditions. And from here on out, I'll be referring to this method as the rail method. But then the second tethering method that we investigated was the rung method. And this was just wrapping the tether around a single rung twice. So as you can see down here, this would be the setup for the rung condition. This was done to investigate if whether the operator tie-off point was located on, if where the operator tie-off point was located on the ladder would influence if a worker could safely descend from the ladder in the case of a fall. So in order to make the drop test simulations more representative of a scenario found in industry, we wanted to control for the surface that the ladder was resting against. We chose a conservative approach and simulated aluminum siding as a worst case scenario. Aluminum siding or eaves trough type material was assumed to have a lower friction of all the one of the lower frictions of all of these surfaces typically encountered with industrial ladder use. So this would be in comparison to a brick surface, wood, or even vinyl siding. So to simulate this type of leaning surface, we custom built adjustable plates that were attached to the support beam that the ladder was resting on, such that the ladder was only contacting the aluminum siding. So you can kind of see it, how it's set up here. And then from this, we built out an anchor point to anchor the ladder off to secure the ladder to, because typically in industry, when you're anchoring a ladder, there's probably not going to be a very convenient side beam located exactly where you want to tie off the ladder to. So we felt that this would be more representative. Similar to the leaning surface, we wanted the ground conditions to also be representative of real industrial scenarios in case ground surface influences stability of the ladder during a simulated fall. So we chose 3 different ground surfaces and tested them in an attempt to replicate different ground surfaces encountered with ladder use. Because we wanted this investigation to be in a controlled laboratory setting, we decided to bring the ground inside. So we developed 3 different, as I mentioned, 3 different ground surfaces: dry level cement, loose earth, and wood to simulate decking. To simulate these ground conditions, we developed some custom made boxes. They were 3 by 2 feet wooden frames, and inside each box consisted of the desired ground condition. So here you could see a setup image of the ladder in the wood decking box that we simulated. We weighed down the wooden box to ensure that there was no slippage when the fall simulation occurred. Here in the images on the right, you could see the loose earth simulated ground surface as well as the cement. Next, our last consideration for applicability to a real field scenario was the direction of force from the simulated 250-pound operator fall. In total, 7 different force directions were tested, with variations in both horizontal and vertical dimensions. Horizontal force directions range from directly out of the ladder, as you can see here, to directly rightward of the ladder, with 45 degrees being the midpoint between the two. Similarly, for the vertical force directions range from downward vertical to a directly out horizontal. Or sorry, directly out vertical, the 90 degrees to the ladder here. While not all of these force directions are realistic of how an operator would actually fall from a ladder, we wanted to see if there were extremes across the force directions that might make a ladder more susceptible to damage or failing. So as a result, we picked these directions to feel kind of like what you would expect for a quarter sphere, where the different force directions filled in the possible extremes of a downward fall that could occur from the ladder. So just for a visual representation, I have here this gray box that would kind of represent where the ladder is. And then these are kind of the fall angles that we tried to simulate a worker falling from any direction within this sphere that they could possibly fall in the downward direction. To simulate a 250-pound worker fall, a custom-made load drop system was constructed. The load drop system consisted of a welded 2-inch square frame equipped with an electromagnet. The electromagnet was fixed to a load carriage subframe, which could be vertically raised and lowered using an attached hand winch and pulley system. Weighted plates totaling 250 pounds, which I'll be referring to this as the load stack, were loaded into a collared sleeve and attached to a steel plate, which was positioned under the electromagnet. When the electromagnet was engaged, the steel plate anchored to the electromagnet and the load stack was supported by the load drop system. When the electromagnet was disengaged, the steel plate was released from the magnet and the load stack was dropped. The entire load drop system was movable and sat on 4 lockable swivel caster wheels. To ensure the entire load drop system did not move during the drop test, the entire system was weighted down using additional plate weights and was then tied off to a support beam using ratchet strapping. To control the angle of force direction, 6 pulleys were attached at various locations on the surrounding walls to achieve angles of pull of 0, 90, and 45 degrees in each dimension. Braided steel cable or airplane cable was strung from the operator tether to the specified pulley to control for the angle of pull, and then attached directly to the load drop system. For the 0-0 condition, which would be a straight down fall simulation, the load drop system was aligned directly underneath the ladder such that the aircraft cable went straight down from the tether to the load stack. So here in the images on the screen, I have an example of the pulley setup for a 0-45 force direction condition. So for this condition, the tether would have been coming straight out from the ladder down at a 45-degree angle. So one end of the aircraft cable is attached to the tether being tested, which in this case would be a rung condition because this tether would just be looped around the rung up here. And then this cable goes down to the wall-mounted pulley. From that, the cable is then fed through the pulley, which is then leaves the pulley and out to the load drop system. So this allowed us to control for the angle of pull here, yet still allow us to simulate that 250-pound drop for each condition. And then here in the image, I kind of have the angle or the tether to pulley displayed in red, and then the pulley to load drop displayed in blue. So to give you a bit of an idea of how we set up a drop test and how they kind of looked, we first attached the cable to the drop tower and lifted the weight stack up. From that, we unlocked the wheels of the load drop system and we very carefully pulled the drop tower until the airplane cable was taut. We then anchored down the load drop system as I previously described. And from that, we lifted the weights up an additional 1 foot to simulate 1 foot of free fall, as we thought it would be unlikely that a worker's tether would be taut with the ladder anchor point. From that, we disengaged the magnet and the 250-pound stack of weights was then dropped, but it did not hit the ground. This was to simulate a worker hanging from the ladder so that we could evaluate to see if the worker could safely descend from the ladder. So here's an example video of the electromagnet being disengaged during the drop test. Once the magnet was disengaged, the load stack then dropped, and to simulate the true fall of the load stack, it did not hit the ground to simulate that 250-pound operator hanging from the ladder. There we go. So as you can see, this would be the additional 1 foot of slack added into the cable from where the load stack would be dropped from. Following each test condition, the ladder was visually inspected for wear, uniformity, or damage. A test was considered a pass if a worker could safely descend from the ladder and the ladder remained structurally intact. If the test was considered a fail, it was a result of ladder failure. A new ladder was retested under the same test condition that elicited the failure. This retesting of the same condition with a brand new ladder was to determine if the failure of the ladder was due to cumulative fatigue from testing multiple conditions on the same ladder or acute failure from the specified testing condition. In addition to visual inspection, all drops were video recorded, which were identical to this video that I'm showing here. And we also had the identifying features of each drop that was being completed in the video, so that if we needed to revisit any of the drops for further investigation, it was possible. So this video here would be a simulated drop of a straight down vertical from the ladder. And you can see here that this would be a rail condition because the tether is wrapped around the rails of the ladder. Now, for the next slide, I have 2 videos that I'm going to bring up. I felt like this first video that I was showing didn't really emphasize how kind of violent the drops actually were. So these are 2 videos that we were fortunate to take with a high-speed camera. So you will see some flickering, but they really slow down the actual drop so that you could see what these drop tests look like and what they kind of did to the ladder. So this one here will be a rail condition. And they're the same condition that I just showed. So again, a straight drop down from the ladder. And then for the rung condition. So in total, 84 different conditions were tested. One of the challenges with this work was that while all of the equipment we used was rated for load significantly beyond that being tested, this equipment that we were using wasn't necessarily equipped to handle repeated violent impacts. So as a result, we broke a lot of equipment. It wasn't not necessarily the ladder itself, but as we progressed through the conditions, equipment consistently started to fail. We had to be vigilant during each drop test and ensure that if there was a fail, it was exclusively due to the ladder. And by the end, we learned that the equipment that we were using almost needed to be rated for almost 10 times greater load than what we were actually testing for. So when a successful condition was completed and we deemed it a successful test, i.e. no broken equipment, the load drop system had remained off the ground, and the ladder had passed, we investigated the ladder as per the protocol described previously. When we deemed the ladder had passed, we moved on to the next condition with the same ladder. A new ladder was only used if the condition resulted in ladder failure. If that was the case, we repeated the tests on a brand new ladder. And this was kind of the approach we felt was easiest to differentiate between cumulative fatigue versus acute failure, aside from buying 84 different ladders and testing them all separately. When we get into the results to kind of look at and see how these two different ladders, the aluminum and fiberglass ladder, performed, I'll first start to talk about the fiberglass ladder and the failures that we did see. So when looking at the fiberglass ladder, there was only one condition that produced ladder failure upon initial testing. This condition was the dry cement ground surface, the rung tether attachment, so just loop twice around that ladder rung, and the 0-0 force direction, so that straight down drop that I showed you in the videos previously. This failed upon initial testing, but passed when we retested the condition. And this was actually the first of the 0-0 drop conditions for this ladder. So during the failed test, the rung deformed upon the load drop and the adjacent rails underwent some slight fracture. So you can see here that this is the end result of what the fiberglass ladder looked like after that failed drop. And this is the rung that the tether was wrapped around. This was determined to be a cumulative fatigue failure. The ladder was extended an additional 2 feet and a retest was performed on the intact rung at the new height. With the retest pass on an adjacent rung, this condition was deemed a successful pass. So this failed test was the first of the 0 straight down drop force directions tested, and it passed on all of the remaining conditions. So you can see here that this is where the ladder failed, and then for the remaining conditions that we tested on that new rung, it passed successfully each time. So this kind of leads us to believe that it wasn't just a one-off that it passed or failed. It was likely due to the 30+ prior impacts that that one rung had endured. So when looking at the aluminum ladder in comparison to the fiberglass ladder, the aluminum ladder performed significantly worse in comparison to the fiberglass ladder. The damage to the ladder was a lot more obvious. Initially, we thought we'd be buying 42 different aluminum ladders for each test. However, this wasn't the case. Specifically, all tests in the 45 and 90 degree, so this would be the 45-degree angle and the directly rightward horizontal force directions, they produce significant ladder deformation above the tie-off location. So the upper portion of the ladder deformed in the direction of the pull force consistently, and when the deformation was inspected after each trial. 2 separate testing conditions produced failures in the aluminum ladder. So the first testing condition that produced a failure was the loose earth ground condition, the rail tether, so this would be the tether around both side rails of the ladder, and the 90-45 force direction. The second condition that produced a ladder failure was the dry cement ground surface rung tether, so this would be the tether just around the rung, and the 45-90 force direction. So again, it was this 45-90 degree off force direction that was really damaging to the aluminum ladder. So you can see here, the first set of testing in the light green here was all completed on one ladder. We then had a very short duration where the second ladder we used was exposed to impacts, and then from that it failed again, and then this darker green shows a separate ladder that we use, a third ladder that we used to finish off the testing. Following failure, as I previously described, a new ladder was used to retest the conditions. Both failed conditions passed upon retest, and the initial failure was determined to be cumulative fatigue failure. Both failure occurrences produced buckling of the aluminum side rails beyond regular deformation observed in the other trials, and some degree of rung deformation or pullout from the side rails. So you can see here, this is an aluminum ladder, and this is the deformation in the ladder. So these dotted lines kind of represent how the ladder should be sitting, and you can see that it's significantly bent off to the right. And then this image here would be an aluminum ladder once we brought it down for further inspection. So this would be a failed ladder. So you can see there's rail buckling here, which is resulting in the rung to actually pull out from the side rails. And I'll quickly go back to the past slide that I had for the fiberglass ladder in a second, just to show you the comparison of what the fiberglass ladder looked like after the testing. So if you look here, this would be an image of what the fiberglass ladder looked like after all testing was completed. So you can see that the one rung here is broken, but it's resting up against a wall here, and you can see there's very little deformation in it, considering that it endured over 40 impacts. In comparison to the aluminum ladder here, which you could see a lot more deformation. So to begin our discussion about the results that we found here in this investigation, results show that given that a ladder is in good working condition and has not been subjected to prior falls or damage, is properly erected and secure, a worker with a mass of 250 pounds or less would be safely restrained and tethered to the ladder as opposed to the lanyard being tied off to a secure structure. And this is based on and inclusive to the test conditions that we simulated here. It's important to note and stress that based on the current regulations, an extension ladder must be properly tied off, and the feet of that ladder must also be properly leveled with both feet making contact with the ground. And again, this is something that we ensured was the case before simulating any of the drop tests. Secondly, it's also important to note that we found that the destruction and deformation to the aluminum ladders was a lot more obvious in comparison to the fiberglass. The failed rung on the fiberglass ladder was actually quite surprising. While we had seen some slight cracking in the fiberglass around the rung, it wasn't obvious that the ladder was about to fail until the test was carried out. In comparison to the aluminum ladder, where it was very obvious and clear that the structural integrity of the ladder was being compromised with the drop tests. So it's important to note that health and safety best practices from the MLTSD under the Occupational Health and Safety Act dictate that any defective ladder should be taken out of service and discarded. In addition, a particular note has been made about fiberglass ladders, which states that the fiberglass ladder should be inspected regularly for cracks and blooming. Blooming is a type of weathering or UV damage that can occur and result in the fiberglass or the glass fibers to become exposed and may not be as resilient as they would be if they hadn't had this type of damage. So this investigation emphasizes that the fiberglass ladders should be closely monitored for damage. Lastly, in terms of the aluminum ladders that we tested, the lowest number of drops prior to a failure was 7. So we did have one, the middle ladder that we tested, that only survived 7 different drops. So this emphasizes that of the critical importance that results from this investigation are based on a ladder that has not been exposed to any high level loading or damage event previously. So throughout the conditions tested, there was minimal wear, uniformity, or change in deformation to the fiberglass ladder. The only visible damage, as I mentioned earlier, was that the fiberglass ladder showed some slight fracturing around where the rails inserted on the ladder. Despite the one instance of rung failure, across all trials tested, there was minimal buckling or deformation. The most drastic deformation was in the 90-degree rightward, so that directly horizontal force direction. However, in these conditions, there was visible flex in the ladder rails in the direction of the pull force. However, once we removed the 250-pound load, the fiberglass ladder rails quickly returned to the original position with minimal deformation. This can be seen here again in the image of that fiberglass ladder that had been exposed to all 42 different drop test conditions. In contrast, the aluminum ladder sustained large amounts of wear, uniformity, change, and deformation and damage across the conditions tested. In general, the rightward horizontal force direction conditions were most destructive to the aluminum ladder, resulting in significant deformation to the aluminum side rails. This deformation ultimately led to the side rails buckling and ladder failure. The deformation in the aluminum ladders primarily occurred above the point where the ladder was tied off. This tie-off location kind of acted as a fulcrum or pivot point, and the ladder was generally unaffected below that point. In contrast to the fiberglass ladder, the aluminum ladder rails underwent permanent plastic deformation and failed to return to the original position following each test, even after we had removed the 250-pound weight from the ladder. This resulted in cumulative and increasing deformation across the tests in the aluminum ladder side rails, and which in turn led to faster cumulative fatigue failure in the aluminum ladder in contrast to the fiberglass. So one last consideration, and hopefully this will open up to some discussion as well, is how well did our experimental setup represent a real-world ladder fall? This experiment tested a wide range of conditions designed to mimic key parameters of a real-world operator fall situation. Based on experimenter observation, force direction showed to be the greatest difference in ladder response between test conditions. The drop tests overall were extremely violent. When looking at the ground surface, this didn't seem to make a difference at all. And similarly for the leaning surface, we didn't observe any dramatic slippage during the drop test that would lead us to believe that one surface would perform better or worse than another. Similarly, the tethering method also didn't really appear to make much of a difference. As I kind of mentioned in the aluminum ladder, we saw a failure in the aluminum ladder with a rung tether tie-off method as well as a whale tether tie-off method. In terms of the fiberglass ladder, we really do think that rung failure was largely due to the cumulative impacts that ladder received. In terms of the force directions, to fully define testing outcomes, we evaluated some very extreme force directions, mainly being in both the horizontal and vertical dimensions. And then we tried to simulate the midpoint in between, which would be that 45-degree angle. The 90-degree vertical dimension forces, which would be directly right to the ladder, may not be a realistic representation of an actual operator fall situation. In the event of an operator fall, it is most likely that the operator would fall directly over the edge of the ladder, which is represented by the 0-0 condition. Or in another scenario, it may be possible that the operator may push off the ladder at the beginning of the fall and have a combination of downward and outward pull force away from the ladder, which we felt kind of was represented by the 45-degree horizontal and vertical conditions. Thus, the conditions that produce the greatest amount of deformation may not be representative of a real fall, but all conditions regardless pass, and results from this investigation indicate that even in these extreme directions, the ladder didn't fail during a single loading event. And the failures that we did see were likely linked to the cumulative drop tests that were being completed on the ladders. So with that, I'd like to acknowledge and thank all of the collaborators that were involved in this study, and open up for any questions or discussion. Thank you.
Kayla, thank you so much for an excellent visual and detailed ladder safety presentation. I'm now going to turn this over to Allison Stevens to facilitate our question and answer period and encourage all of our participants to put your questions into the chat box. So over to you, Allison.
All right, thank you. Hope everyone can hear me. I'm off mute. We do have, first off, I can see why this is totally terrifying, Kayla. Thank you for, exposing us to this. I don't even think many of us would have even thought through that. So really lovely to learn all that stuff. We have a question from Andrew. Did the use of pulleys for some of the drop tests offer a mechanical advantage that reduced the test load of 250?
That's a great question. I don't believe so. The pulleys didn't really have, they were free to move however they wanted to move. when the airplane cable went through them. So I don't think that that would have been an issue. They were really just there to control the angle the angle of pull that was occurring when we did the drop test. Yeah, so I don't think it would have been a huge difference. And we didn't use, another consideration is also we didn't use the pulleys for the straight down test, and the ladders didn't also didn't have an issue passing that passing the straight down drop test, which the airplane cable would have been attached directly just to the load drop system.
Okay. I would imagine that the actual vertical forces will be greater than 250. Can you please provide an estimate ground reaction force? Wow, he's asking you to do math. Peter.
I don't have that estimation. I think that this is something that I think we've talked about a bit with IHSA during our meetings. I don't have an estimate offhand of what. We also didn't have a force transducer directly connected in between the load drop system interface. It's definitely something that we could look into further as this study progresses, unless like right off the top of my head.
Right. Now, I guess, from my own perspective, then I think you alluded to, these are rated at 250 or rated at 200 pounds. You kind of hinted that maybe that rating is not the best representative of the safety factor that it would provide. Can you maybe elaborate on that a little bit?
So you mean that like based on the fact that,
yes, do you feel that the 250 rating and the 200-pound rating that these ladders have, do you feel that that is the correct rating, or is that something that we should look at?
I definitely, based after conducting this study and seeing how much the ladders can handle, I definitely think that it doesn't need to be lower than that. I mean, I was flabbergasted at how many drop tests that fiberglass ladder was actually able to withstand. I mean, we use that ladder as well for a lot of the pilot testing. So the amount of drop tests that ladder would have experienced was well over the 42. And even just reviewing the video from the drop tests, there really wasn't any indication, even by that last test, other than that one rung failure, that really led us to believe that the ladder was going to fail. Similarly, for the aluminum ladders, I was actually shocked that they did quite well with the single drop test. It was that repeated vertical or 90-degree force direction that was really damaging to them, which again isn't really that representative of how a worker would fall. A worker isn't very likely to just kind of jet out at a 90-degree angle from the ladder when they're falling. But the fact that it did withstand even one test, I was quite surprised, pleasantly surprised. So I think that 250-pound rating is justified. Yeah.
Great. Well, and that kind of leads into the question, based on this research finding, do you see any changes in regulations related to the ladder tie-off?
It's definitely something that we've discussed with the collaborators, so IHSA in particular. I guess it really depends on, do we think that just this testing is sufficient, or should there be another stage of testing before we're telling workers that they can actually do this? But it's definitely pointing in the right direction, that it could be something that might change. And I think, again, almost doing the cumulative impacts on the same ladder almost provides evidence that it's likely that a ladder that hasn't been subjected to high rate loading, it will likely sustain a worker fall. But again, this was just based on simulated drops. We didn't have an actual person falling from it, with some variability that might occur when an actual worker is falling.
Okay, good. How long is the study for, and will you be expanding the scope of the research based on the results that you found?
How long is this study?
How long is the study for? Like, is it's completed?
Oh, yeah.
Or,
Yeah.
and,
So it's completed.
Okay.
So it's completed at this point. For the foreseeable future, there isn't any talk about expanding it further. I think we're kind of going through the results that we have now and just trying to kind of digest and see there might be any next steps before moving this forward to being something that might actually be possible in the ladder safety and preventing falls.
Great. And Peter has brought up that, would you be able to present this information to the CSA Z11, Z11 Ladder Standard Committee? You saw my little American slip in there, sorry. Z11 Standard Committee.
Definitely. I mean, the evidence is there. We have every drop test on video, so we do have a lot of research evidence to show that what these ladders can sustain. So it's definitely a good point, and probably something that would definitely be possible if it's an area that both myself, Dr. Callahan, Dr. Dickerson, and the collaborators on this study would like to proceed with.
Great. And we have kind of one more or another question regarding the tether point. The question from Nathan is, if the tether point was closer to the tie-off point of the ladder, it would make sense that the deformation stress on the ladder would be less. Was this looked at in any way, or really from a kind of the standpoint, what is the easiest tie-off point, and would you recommend tie-off to the rung or the side rail after doing this investigation?
The tether point. I'm just trying to
Yeah,
I'm just trying to reread the
chat?
question.
Okay,
Yeah.
good.
The tether point is closer to the top. Oh, so meaning like if where the ladder was tied off based on like I guess where the tether was located. Yeah, that's a good point. In terms of the that might have made a bit of a difference. It wasn't looked at first to answer the question. So I think what Nathan's asking is if we moved the tie-off location for the tether closer to where we had tied the ladder off to the structure. So we kept the tether location consistent. And in terms of the rung tie-off method, I don't think it would have made much of a difference. If I can go back to this image here. So with the rail tie-off method, it didn't really matter. Like when we set up the test condition, the tether was centered in the ladder, across the ladder, and it didn't really matter that it was centered. When we pulled on it, especially with those like sideways forces, the tether just went flying to the right side of the ladder, if that makes sense. So I think for those conditions, I don't think it would have really made a difference.
Sure.
In terms of, do I think,
would you recommend tie off to the rung or the side rails?
Yeah, I don't think I would really recommend one more than the other. As I kind of mentioned in the presentation, both tie-off methods seem to pass, and we pretty much had consistent, if a ladder did fail, it wasn't that it always failed with a rung tie-off. I mean, there were 2 rung failure tie-off methods, and I believe 1 rail tie-off method, or no, it might be 2 and 2, but it was fairly consistent, and 1 didn't seem to result in more damage to the ladder than the other, especially when it's an isolated drop of a fall event, if that makes sense.
And I did seem to skip over one question here. Does the number of times a ladder is used impact its integrity? And I guess that question is just used versus a fall. I know you said that 7 drops is kind of your
what the aluminum ladder anyways could that isn't something that this investigation exclusively looked at. I did look through some of the regulations, and there wasn't really anything in those regulations about specific like timeline usage for ladders. But what I did read and kind of allude to in the presentation is that the fiberglass ladders kind of need to be monitored, because I guess that, or in particular that cracking or that weathering of them is possible, and it's not obvious like an aluminum ladder. I mean, if an aluminum ladder is deformed, it's very obvious, but not so much in the fiberglass. So I'm not sure about the length of time, or if duration of time would, like at what time point a ladder might become an issue in terms of wear and tear. But definitely it's recommended that the ladders are thoroughly inspected before they're erected and used, regardless if a worker is tying off to them or not. Okay. Which at this point, a worker shouldn't be tying off to them, because it's still regulation to tie off to a sound structure.
Okay, good. Just a few kind of questions. You know, the one that the rung actually did detach, did that worker actually, would that worker have hit the ground?
With the rung fail, yes, yes,
Okay,
definitely. The load stack came crashing down and smashed into the ground.
onto
So
the
yes,
ground.
yeah, yeah,
Okay,
yeah.
that was a good one, Mike.
Mhm.
Yes, that would be a fall.
Yeah.
And then Hollins, if the load drop travel distance was 12 inches, have we considered how the results would factor in the load acceleration for a longer drop distance?
So
Longer
that's a
drop
yeah,
distance,
yeah,
travel
so that
distance.
so
Yeah.
that's a great point. So that I believe that's referring to the free fall that we allowed the load drop system to experience. So
Hmm.
that is a good point, and it was something that we thought about. We added that 1 foot because we thought it was somewhat representative. Definitely having a larger amount of free fall would definitely and likely influence it. We were kind of maxing out our load drop system with how high we could get those weights up off the ground, because to ensure that the load drop system didn't actually smash into the ground, simulating someone hitting the ground, and that it was actually hanging there, we had to raise it up fairly significantly before we even invoked that 1 foot of free fall in the load drop system, because for some of the trials that we simulated, and I didn't show the video here, but some of those really direct pull forces, like where we were pulling directly out at the ladder was pivoting, so that would add a lot of extra slack into the system that we need to account for before we set up the load drop system. Now the ladder still stayed upright and structurally sound, and a worker would have been able to descend, but we didn't really have the ability to go much higher than that 1 foot of free fall.
Sure. Well, that kind of leads to the future research. What research questions would you like to answer given these findings?
Oh, that's a good question. I think my logical next step would be using some kind of um, and I'm not sure how you go about controlling this, but would be using some kind of a more operator similar, like essentially I'm thinking like a crash test dummy or something to actually fall from the ladder to actually simulate like more human like behavior. The load drop system, like I said, we kind of use the system to get pretty much that quarter sphere to look at all the force directions just to see how the ladder would hold up. But I definitely think adding some kind of load drop where there is some more variability in how that load would fall would definitely be a next step.
Excellent. And then we have Mike asks, did any of the side rail tie-offs result in a fall?
Yes, in the aluminum ladder. These tie-off methods were particularly damaging to the aluminum ladder, uh, particularly for those rightward force directions. They've really significantly deformed the side rails, which caused the rails to pull out evidently at for the failures. But yes, they did.
Okay. And then, I just a question. I know we always had to do a visual check of all ladders that we used at Ford. And so do you feel, I think maybe in aluminum you would, that the visual checklist that they go through is adequate to be able to tell whether or not the ladder is good for use?
Huh. That's a great question. I'm not sure off the top of my head.
Sure.
I think it would really depend on how well, in particular, I'm thinking for the fiberglass ladder,
Hmm.
it would really depend on how well a worker is trained to look for damage. Because the fiberglass ladder, before that drop test, as I said, it wasn't really that obvious that there was damage to the rung, around the rung. Once you brought the ladder down and someone pointed it out, and
Hmm.
someone had pointed it out to you, that was fairly obvious. I mean, with the aluminum ladders, I think anyone would be able to tell that they were damaged.
Right. It's
So that's,
even just looking
yeah,
at this picture, I'm like,
yeah,
okay,
yeah,
in some respects, I know that I shouldn't use that aluminum ladder, right?
yeah,
So
exactly.
interesting.
Yeah, so I think it would definitely depend on how the workers are trained, and that actually might be another study is how much we're assuming that these ladders are in perfect condition. We bought that fiberglass ladder; it was brand new, but even like a couple months of use. What are the conditions that have been used in? Those are further questions to see how those may influence the structural integrity of the ladder.
Great.
I have one last question just before we wrap up, and that is, based on your research findings, do you see a change in regulations related to ladder tie-off forthcoming?
I mean, we certainly showed here that it is possible for a ladder to withstand a 250-pound operator falling. At the current time, we're looking to publish the work here, and so that it can be kind of publicly accessed, the findings that we found here. But it's definitely something that I think has a basis for moving forward, whether we have enough evidence here to put it into practice, or if more work needs to be done. I think that's something that we can discuss further with the industrial or the collaborators on this project.
Thanks so much, Kayla. And I think this is a great opportunity to say thank you to everyone today for joining us. Kayla, for your great presentation. It was extremely visual and detailed and gave us a wonderful overview of ladder safety. And I'd also like to say thank you to Allison for facilitating the question and answers. I'd like to encourage all of our participants to fill out our evaluation, and please join us for our next webinar in our wind energy webinar series. It will be the second webinar in that series, and it's being offered free on July the 8th. Green Ergonomics, a global perspective on the wind energy sector. Does experience matter? So thank you all for joining us today. We look forward to seeing you on our next webinar, and please watch for more webinars jointly brought to you by CRE-MSD and ACE. Have a great rest of the day.